So I wanted to start by saying a few more words about some of the problems we talked about yesterday and didn't get a chance to really discuss.
The chalk is stolen.
What?
The chalk is
The
stolen.
chalk is gone.
It's stolen.
And we moved the table.
Okay.
I'm seriously disoriented. But we'll just have to soldier on, I guess.
Sorry.
So the first thing is a problem that is, of these three, this one is in some sense completely straightforward given the solution to the problem about lines on a cubic surface. The idea is that you approach it in exactly the same way. You look at the space of lines in P4, and you ask how many are contained in X. So the first thing you need to do is to describe the Chow-ring of the Grassmannian of lines in P4. And that is, as I said last time, a good exercise. We worked that out for the Grassmannian of lines in P3, and if you follow that, you can basically carry out the same process in P4, for the Grassmannian of lines in P4. Once you've done that, you can introduce the corresponding vector bundle, whose fiber over a point L in the Grassmannian is simply the space of quintic polynomials on that line. And you see that the answer to this question is the top Chern class of that vector bundle. And then you calculate the Chern classes of that vector bundle by the splitting principle. So it's very much analogous to what we did. And if you want this sort of exercise to, really cement your understanding of this technique, this is it. I'm not going to do it. But it also raises, I also asked another question here, how many twisted cubics? And that, I did not want you to go ahead and try to do. It's in fact quite difficult. The point was to raise the issue of thinking about how you would approach this problem. And the thing is, the first thing that you would have to do, an analogy with what we did in the case of the problem involving lines. By the way, I should say that you do, if you make a dimension count, a naive dimension count, the same sort of incidence correspondence between twisted cubics in P4 and quintic hypersurfaces, you see that you do expect a finite number. Okay? The first thing you would need to do is to introduce a parameter space for the space of twisted cubics. And you would have to then describe its Chow-ring and go on from there. But that is a highly non-trivial problem. Just trying to find a suitable parameter space for twisted cubics, and that's what I want you to think about. Robin mentioned in his first lecture this week the Hilbert scheme of twisted cubics in P3. This is in P4, but it's not that much different. And he mentioned that there are all sorts of degenerate twisted cubics, and there's a second component even of the Hilbert scheme, which is larger dimensional and just messes everything up. It's a complicated space. And to make matters worse, all our intersection theory so far has been predicated on the idea that the parameter spaces we're working with are smooth. Now that's a real problem. And I just want to make this point because one of the people who solved the problem is now in the audience. The issue is this. Robin gave you a very nice description, a very calculable description of the tangent space to the Hilbert scheme. And if you look at a smooth twisted cubic, if that's not redundant in your vocabulary, as Robin suggested, you can, as an exercise, you can calculate the space of global sections of the normal bundle and see that, in fact, it is 12-dimensional, and conclude that the Hilbert scheme is smooth at that point. But think about it. The Hilbert scheme, as Robin said, has two irreducible components. Where they intersect, those are necessarily going to be singular points of the Hilbert scheme. In fact, if you calculate the H0 of the normal bundle at a point of intersection, for a curve, or a subscheme, I should say, corresponding to a point of intersection of these two components, you will necessarily see that the dimension of the Zariski tangent space is 16. It's a point in the union of a 12-dimensional component and a 15-dimensional component. So the Zariski tangent space has to have dimension at least 16. In fact, it does have dimension 16, but that doesn't tell you anything about whether the individual components are smooth at that point. Now, when we want to work with a parameter space for twisted cubics, we might want to take, for example, just the irreducible, the 12-dimensional irreducible component. But how do we know whether it's smooth at that point? That requires a much more delicate deformation theory calculation involving explicit calculations of obstructions. And that was worked out by Rodney Peony, who's here today, and Michael Schlesinger. And so that does tell us at least that this space is, the space, the Hilbert scheme at least, of twisted cubics in P3, the component we're interested in, is smooth. But that's just the beginning. And then you have to calculate its Chow ring, and of course we are here working in P4, and that does involve some additional wrinkles. It turns out to be a very complicated calculation. I won't, oh hell, I'll tell you a story. This was the actual number of twisted cubics on a general quintic threefold was worked out by Guerre and Ellings. Do you remember when that was exactly? It's the 80s or something, sometime in the 80s. And then, people had previously worked out the number of lines, and conics likewise. And then twisted cubics were substantially, several orders of magnitude harder than Guerre and Ellings who did it. And that was that until a few years later, the mathematical physicists discovered an interest in this question. This turns out to be a number that you can predict using the theory of mirror symmetry in physics. And so the physicists had used this theory of mirror symmetry to predict the number of rational curves of each degree threefold. And their numbers agreed with the classical numbers for lines and conics, but disagreed for twisted cubics. And this caused quite a stir, and nobody could figure out where the discrepancy was coming from for several years, as I recall. Eventually, it didn't take that long.
It didn't take that long.
Okay.
There was a mistake in their program.
Exactly. The point is, what Guerre and Ellings had done, the actual physicists got the right number, right? But what Guerre and Ellings had done was completely correct from a mathematical point of view. It's just that the calculation in the Chow ring of the space of twisted cubics that they were using, the parameter space that they were using, was so complicated they had written a little computer program to carry out the calculation, and there was a mistake in the program. But the main point of this all is that this is not a problem to undertake. Like, this one is. Anyway, the other point, I mean, there were the two main reasons I mentioned this problem. One was, of course, to involve twisted cubics. The other was to suggest that one of the aspects of doing enumerative geometry or intersection theory is the problem of finding a suitable parameter space for the objects you're looking at. And the real content of today's lecture will be really, in some sense, the first classical example where this issue came up. And it was in response to this question. Okay, one last thing before we get into that. I wanted to just explain something I said last time about this problem. I said that this problem also involved Chern classes, and I just want to set it up to show you how this involves Chern classes other than the top Chern class. Okay? And it's very straightforward, but I think it's worth saying. The point is this. You remember how we set up the problem with cubic surfaces? I want to do something analogous. I want to look at, so this is now in response to this third problem. And I want to introduce a vector bundle of rank 5 on the Grassmannian of lines in P3 I guess I want to give that vector bundle a name, and for some reason E seems to be the name of the default name for a vector bundle. I'm not sure why that is. I want to characterize it by saying that its fiber at a point L in the Grassmannian is simply the space of homogeneous quartic polynomials on the line L, or again in Ivan language, H naught of O L of 4. Okay? So that's a vector bundle. It associates to every point in this Grassmannian a 5-dimensional vector space, and that vector space varies, you know, in a fairly natural way with the point or line. The other thing is that if we have F, a homogeneous quartic polynomial, on all of P3, a quartic polynomial in all 4 variables, we get a section of this vector bundle, which I'll call tau sub F. And that's defined by saying that its value at every point L is simply the restriction of F to L. So that gives me a global section of this vector bundle E. Okay? This is a section, I should say, of E. Now, in the situation we have, I mean, of course, we have a vector bundle of rank 5 on a 4-dimensional variety. We don't expect there to be any zeros. And that corresponds to the fact that we established yesterday that a general quartic surface in P3 contains no lines. We know that. But now, suppose I have a pencil of quartic surfaces, right? And if I do, so that means I take 2 general quartic polynomials, and I ask how many of the quartic surfaces in that pencil. I mean, you can think of it in the space of all quartic surfaces, which is a P34, as just a random line. How many do contain some line? And the answer is, again, using the notation from that problem, that ST contains, okay, so let me just say it. The number of lines contained in some member of the pencil is just the number of points L such that tau F of L and tau G of L are linearly dependent. You see, if these 2 restrictions are linearly dependent, that means some linear combination of F and G vanishes identically on the line. And the line correspondingly lies in the corresponding member of the pencil. Since this is a general pencil, no line lies on more than one element of the pencil. Otherwise, it would be a component of the base locus, and the base locus is smooth. So the conclusion is that the number of lines in the number of elements of the pencil containing some line is equal to the number of lines contained in some element of the pencil. That's the number of points in the Grassmannian where these 2 sections are linearly dependent, and by our definition, that's the 4th Chern class of the bundle E. And now we're set. We can go ahead and calculate this exactly the way we calculated the Chern classes of the bundle we introduced for cubic surfaces. So this is now, I mean, having set it up this way, this becomes just another exercise in the splitting principle. Again, worthwhile. So any questions? That sort of concludes. I'm sure there's much more to say about the topics we took up yesterday, but I want to put that aside for now. So if there are any questions, this is the time.
So you could do the same thing with the number of lines on a septic 4-fold in T5.
Yes, exactly. If you look at if you look in general, I mean, what we saw was that if we look at a hypersurface of degree D in Pn, we expect a finite number of lines, and in fact, there will be a finite number of lines on a general hypersurface of degree D in Pn, exactly when 2n minus d minus 3 is 0. And so, or in other words, n is equal, well, let me not try to fiddle with that in my head. The examples are the lines on a cubic surface, lines on a quintic threefold in P4, as Robin says, a septic fourfold in P5, and you can calculate all these numbers. And I don't know a closed form expression for the answer, but it's interesting.
Sorry, what do you think you expect that for the surfaces that contain lines will be only one?
That's, okay, so that's a very good point. The question is, if we really are literally counting the number of elements of the pencil that contain a line, why is that the same as the number of lines contained in some? What if some surface in the pencil contains 2 lines? That's a very good point, and that has to be addressed. What you have to do to answer that question, and of course I'm not going to do it right here, but it's a straightforward exercise. What you want to do is look at the locus. Again, think of this as taking place in the P34 of all quartic surfaces. We've seen that the locus of quartic surfaces that contain a line is a hypersurface, and we're trying to calculate its degree. What you want to do now is look at the locus of quartics that contain 2 lines. And I claim that that locus has codimension 2 in P34, which means that a general line in P34 will miss it. Now that's again, it's a very nice exercise. You have to be a little bit cautious because you set up a similar incidence correspondence where you look at pairs of lines and a quartic surface containing them, and you calculate the dimension. But you notice now that the space of quartics containing a pair of lines, it's always a linear condition. It's always a sub-projector space of P34, but the dimension depends on whether the 2 lines are incident or not. So you actually get 2 irreducible components in that incidence correspondence, but they both have dimension 32. So it's a nice exercise, and if you like playing around with incidence correspondences, it's a good way to sort of test that aspect of the technique. Okay, so thank you for bringing that up. Any other questions?
So maybe, Joe, a
Yeah.
comment is that
Yes.
one can ask a similar question for, conics. How many conics?
Yes.
How many surfaces?
Exactly. If you have a quartic surface, if you have a pencil of quartic, now we have not established the basis for that question. The question Chiro asks is, if you have a pencil of quartic surfaces, like we do, a general pencil, how many contain a conic?
Or a cubic?
Or a twisted cubic, yeah. What this is not, what we haven't established is that we would expect among all quartic surfaces, those that contain a conic to again be codimension 1. And those that contain a twisted cubic, again, is codimension 1. And you can, each condition corresponds to a hypersurface in the space P34 of quartics. And you can ask for the degrees of all of these. And once more, I think the mathematical physicists have gotten involved in this. But you can also, for the case of conics, because we have a good parameter space for conics, that will come up tomorrow. We can answer that question explicitly purely within the realm of sort of elementary intersection. When you get beyond conics, it gets much trickier. Rodney, do you happen to know if that's worked out for twisted cubics? Now that's a very, very good problem. And if we have time tomorrow, maybe once we've introduced a parameter space for conics in P3, we can sort of at least set up the problem and make it, sort of see what calculation you would have to carry out to answer. So, it's a beautiful picture. And it also touches on a phenomenon that was discovered first by Max Noether, that, whereas a quadric or a cubic surface in P3 contains all sorts of curves on it. Conics, twisted cubics, they're all there. When you look at a quartic surface, what you see, and think about what we've just said, a general quartic surface, a general quartic surface contains no lines. If you do the dimension count, you see a general quartic surface contains no conics and no twisted cubics either. In fact, a very general quartic surface contains no curves at all, other than complete intersections with that surface. That was a theorem, I guess it was first stated by Max Noether and proved by Lefschetz. I don't think Noether ever proved it.
Yeah, I'm going to talk about that next week.
Oh, you are? Okay.
That's the topic of my talk at my home.
Ah, okay. Hold on. Okay. So I will stop there. So I'm going to move on now and talk about the five conic problem, which, as I said, is sort of historically one of the most significant problems in the development of algebraic geometry, certainly of intersections. So,
Joe,
yeah,
you said the quartic contains in general no rational curves,
yes, a very general quartic contains no rational curves.
but I'm sorry, this book, I thought that.
Oh, I'm sorry, no smooth rational curves. I said, what I said was, and I'll stand by this much at least, that every curve is a complete intersection. So you have, for example, intersections with a plane. Now, among those are a finite number of rational curves. So, for example, you have tritangent planes to the surface. You know, if you take this quartic surface and you just drop it on the floor, it comes to rest on a tritangent plane. And that plane section of the quartic will be typically a curve with three nodes, a quartic curve with plane curve with three nodes, which will then be rational. And the same thing is true for quadric sections. There'll be a finite number of rational ones. And so you do get rational curves, but no smooth rational curves, I should say. And in particular, no curves other than complete intersections. So. And again, there will be, of course, special quartic surfaces that do contain such curves. All right. I have a feeling I'm going to regret the time we spent, but I don't right now. I'm glad we could talk about those things. But now I want to focus on the five conic. And it's a very natural problem in some sense, if your mind works that way anyway. It's, if we look at the space of conics, as we have said repeatedly this week, they are parameterized by a five-dimensional variety, in fact, just P5. And it's, so to speak, one condition in the classical language for a conic to be tangent to a given conic. So we would expect a finite number of conics tangent to five conics, and it's not hard to see that there are, in fact, a finite number of smooth conics tangent to five conics. So the question is how many?
By the way, you don't have to say smooth. There's no way two lines could be tangent to five general conics.
No, but I have to worry about what we mean by tangent.
Oh.
So we'll talk about that, and that in some sense is exactly the issue we want to raise here. When I talk about a smooth curves, I mean, these are general conics, C1 to C5, so they are certainly smooth.
Right.
And so when I talk about two smooth conics, I know what I mean when I say they're tangent, but it's less clear what I mean when they're singular. So we have to, so we will address exactly that issue. Yes, I'm sorry, my mind was still on the right-hand board when I was writing this. P2, thank you very much. That made no sense at all as it stood. Okay. So, one of the perks of getting older is that you sort of are allowed to reminisce and tell stories. And people are too polite to sort of yawn visibly. But I wanted to tell you about my experience with this problem, because it was really, it was a real turning point for me too. When I was a graduate student, I spent a year in Berkeley. My advisor, Phil Griffiths, had gone out there on sabbatical, and I tagged along. And Robin and Arthur Otis were just extremely nice to me during that year, and they really, I learned a tremendous amount talking to them. They were very generous with their time. And one day Arthur, who I'd been talking to, came and said, you know, there's this interesting problem. You should try to do this. if you have five general conics in the plane, how many conics are tangent to all five? And I said, that doesn't sound so hard. And no, seriously, it doesn't. I mean, the point is, what you want to do is you want to look at the space. You need a parameter space for conics. Well, Lord knows we have it. We've got P5, the space of all conic curves in P. And inside that, we'll take Z sub C, for example. For any smooth conic, will be the set of conics tangent to C. And as Robin raised the question already, it's not necessarily clear what we mean by saying a singular conic is tangent to C. So what I want to do is maybe just take smooth conics tangent to C and take the closure. Okay? So in any case, this is a hypersurface. And we're simply asking, what is, if I take 5 such hypersurfaces corresponding to 5 general conics, how many points do they intersect in? Now that's, as an intersection theory problem, that seems pretty trivial. It's just you're intersecting 5 hypersurfaces in P5. Bezout tells you the answer once you know the degree of these hypersurfaces. So let's figure that out. We don't have the answer. Well, it's not hard to do. There's many ways to do it, in fact, but I will just sort of suggest one. If we have, the question is, what's the degree? Of ZC, and equivalently, we can ask if we have a general pencil of conics, right, a line in that P5, how many points of intersection does that line have with the hypersurface? In other words, in a general pencil, CT of conics, how many are tangent to C? Well, there are many, many ways to do this. You could take the conic C, the fixed conic, and parameterize it by P1, and then just take these the equations of these conic curves and pull them back to P1. You get a pencil of degree 4 polynomials in one variable. And the coefficients of those polynomials are then just linear functions of a parameter t. So think of this. We have a quartic polynomial in one variable whose coefficients are linear functions of t. How many times do you have a multiple 0? In other words, what's the degree of the discriminant? The discriminant of a quartic polynomial is a polynomial in its coefficients. What's the degree of that polynomial? Seems like a basic question. And in fact, the answer is well known. In this case, it's 6. If you want to say it a little bit differently, but it amounts to the same thing, we sort of say, let's give these guys names, these conics, CT. We can write them, as we did long since gone, we can write these as the 0 locus of a quadratic polynomial. So you call it Q, T naught Q plus T1 Q prime in the plane. And then another equivalent way to express this to say that the ratio Q over Q prime is a rational function on the curve C, which gives a map from C to P1 of degree 4. So this is a degree 4 map. And the conics tangent in this pencil, tangent to C, correspond to branch points or ramification points of this map. So the number of ramification points by Riemann-Hurwitz is equal to 6, and again, that tells us the degree of the hypersurface. In fact, this is more or less the same argument in just in a geometric form. And this is, if you asked me to calculate the degree of a discriminant in general, I would use Riemann-Hurwitz. So, okay, but this is a hypersurface, and now we know it has degree 6. So the answer is simply 6 to the 5th by Bezout, or 7,776. And, you know, I don't remember how long it took me, but it, you know, I was a little suspicious because it seemed simple, and Arthur usually asked me harder questions than this. So I went back and I told Arthur the answer was 7,776, and he said no. And I said, no, I'm sure of this. I checked it, and well, I didn't check it by writing out the 7,776 pounds. But he said, no, you're wrong. And it really bugged me. And I spent the rest of that day and most of that evening, most of that night, in fact, trying to figure out what was wrong. In fact, if you think about it, it's once somebody you trust tells you this is the wrong answer, and you really are forced to think about what could be wrong with this calculation, it's not hard to spot the problem. Let's see which, oh yeah, this is it. The problem comes down to the issue that Robin raised. What do we mean by tangency? Well, we gave a definition of tangency, and in some sense it's the only possible definition. We want these to be closed hypersurfaces. They certainly want to include smooth conics tangent to C. So we just take the closure. It's the simplest thing we can possibly do, and the smallest. But if you think about it also in terms of discriminants, what we're asking for, this amounts to, is the set of conics here, and I just now mean all possible conics, such that C has a non-transverse, Z sub C is the set of conics D, such that D has a non-transverse point of intersection with C. In other words, it fails to meet C in 4 distinct points. And that necessarily includes all double lines. You see, when we talk about the P5 of conics, that includes smooth conics and pairs of lines and double lines. And a double line, by our definition, is tangent to every conic. It cannot meet a conic in 4 distinct points. So, again, if we think of this as, again, let me just try to rewrite this again. D does not meet in 4 distinct points. That certainly includes all double lines. Now, in the space P5, the set of all double lines is a surface, naturally, isomorphic to the dual projective space. For every line, we can take its double, which is a conic. And it's not hard to see, in fact, that this is simply a copy of the Veronese surface. So we have this surface. The fact that it's a Veronese surface is not going to be relevant, but it's amusing. The main point is we have this surface. And all these hypersurfaces we're trying to intersect contain that common surface. In fact, the intersection for C1 up to C5 generally, the intersection of the corresponding hypersurfaces consists exactly of the Veronese surface, the surface of double lines, union a finite set, and this being the finite set of solutions. In other words, smooth conics tangent to all 5. There's, as Robin points out, and it's again a nice exercise if you like to play with projective geometry, no conic consisting of a union of 2 distinct lines can be tangent to each of 5 general conics. So the intersection consists exactly of the intersection we're really interested in, the smooth conics tangent to all 5, plus this surface. And the problem is because this surface is here, these 5 hypersurfaces, ZCI, can never intersect transversely. And so Bézout does not, in fact, apply. So let's take a moment out now and think about what we're going to do about this. And there actually are a number of solutions, a number of ways of dealing with this. And I'm going to show you one in particular, which is a very beautiful classical construction that exactly addresses this issue. But I just want to talk for a minute about other possible solutions. What would you do if you had a collection of hypersurfaces, in this case in a simple variety, P5, whose intersection contains a component too large? Well, for me, the first thing I thought to do was what you do almost automatically when you have an intersection you want to get rid of is you blow it up. Okay? So let me list here possible solutions. And first is simply blow up S. In fact, that works. And that's in fact how I answered the problem. Once I figured out what the problem was, this is actually what I carried out. And again, it's a nice exercise. So in other words, we let P5 tilde be the blow up along S of the P5 of conics. We let ZCI tilde be the proper transform of the hypersurface ZCI. And now the hope is that by blowing up S, you eliminate the excess intersection. And in fact, that turns out to be the case. If you work it out, you'll see that when you blow up S in P5 and take the proper transforms of these hypersurfaces, then the intersection consists entirely of this finite set. You've eliminated all the points of intersection corresponding to, or lying over in this case, double lines. So in fact, the answer then becomes basically the five-fold self-intersection of the class of this hypersurface, the proper transform, in the Chow ring of this blown-up P5. So what you need to do is to calculate the Chow ring of the blow-up and find the class of this proper transform, and then calculate its fifth power, take the degree of that class. So that's process number one. And it works. And if you want to see this carried out, by the way, I think it's in Griffiths-Harris in the chapter 6. You can see how to do this. In fact, you can get away with a little bit less. You don't need to know all of the Chow ring of this blow-up just to calculate this five-fold self-intersection of this class. But okay, let's leave that. That's the first solution. The second, which I'm really not going to talk about, is to apply what's called the excess intersection formula. And this is a good occasion to talk about the relationship between what we're doing this week and, for example, Fulton's approach to intersection theory. Our approach to intersection theory has, from the beginning, been to prove and invoke a moving lemma. Well, invoke, prove. But it's the idea is that given two equivalence classes of cycles, we can find representative members of those classes that do intersect transversely, and then we define the intersection to be the intersection of those classes. There's a number of drawbacks in this approach, if you're serious about doing intersection theory. In a way, it's a way to get up and running quickly and sort of see what intersections are about. But there's a number of drawbacks long term. And for one thing, the moving lemma is not deep, but technically very demanding. It's a long sort of argument with a lot of details. The other thing is it restricts you absolutely to working on smooth varieties. If you're working on a singular variety, the moving lemma does not hold. If you have something, even a simple singularity, like a cone over quadrant cone, a cone over a smooth conic curve, right? If you look at something like the cycle given by a line of the ruler, you see that passes through that singular point, and you cannot move it away. If you think about it, there's no cycle rationally equivalent to this line. Even allowing positive and negative coefficients, there's no cycle whose support doesn't include this singular point of S. So if I want to intersect two of these lines, two rays, I cannot move them away from that common point. They will never, no two representative cycles for these classes will ever intersect universally. And in fact, you can see that already it leads to a problem. You see, if I wanted to know what's the intersection number of these two curves? Well, it looks like 1. But there's a problem there. That's the self-intersection of the curve. All the curves in this, the rays of this cone are rationally equivalent to one another, right? So we're really asking for the self-intersection of this class. If I take, say, the sum of those two, though, right? The sum of those two forms a plane section of the quadrant. And that can be moved away. That can be moved away. So if I call this L and call this M, I have L plus M is equivalent to a hyperplane section. And the hyperplane section, I can say this is a good representative cycle for the hyperplane section. That visibly meets M in one point, and it meets L in one point. So the question now is, since L and M are rationally equivalent, right, this would say that L dot M is 1/2. In other words, L meets twice L in one point. So we get into trouble. And okay, in this particular case, we can get around it simply by allowing rational coefficients, but in general, we can't, and the moving limit fails. So our approach has restricted us, absolutely, shackled us to working with smooth protective rod. That's not necessary. One of the Fulton's great insight was that you can set up intersection theory in a way that does not require the smoothness of the ambient space. You do need some restrictions. You have to restrict yourself to a certain class of cycles. You can't just intersect two arbitrary subvarieties of a singular variety and have the intersection be invariant under deformation. But you can intersect a certain class of cycles, including, for example, local complete intersection cycles, because they have a good deformation theory. You can intersect those with arbitrary cycles. And so Fulton sets this up. And part of what he does is he introduces an excess intersection formula. He says if you have two cycles on an arbitrary variety, not necessarily smooth, as long as one of them is a local complete intersection, for example, then you can describe the intersection class, even if they intersect in the wrong dimension. So rather than try to take two cycles and move them until they meet transversely, he just says, let them be. Keep them where they are. I can describe for you a class associated to that intersection of the right dimension, even if the actual intersection has the wrong dimension. And this is the excess intersection formula. In some sense, it's one of the cornerstones of Fulton's approach. And from many, many points of view, this is a superior approach to the whole problem. So I urge you, if you want to see this, to take a look at Fulton's book, where he develops the whole subject of intersection theory in a way that allows him to do much more, intersect much more generally than we do.
But still, neither of these questions will answer your question, because the moving line answer is obvious. We can move the 5% in general position, and then we get 7,776, which is the wrong answer. So,
no, that's true. That's exactly the point. I'm saying what I'm saying about the excess intersection formula is Fulton actually has a formula that you can apply in this circumstance.
it'll tell you.
And it'll tell you what Fulton does is when you have an intersection and you write it as a union of components, some of which may have the wrong dimension.
Yeah.
Fulton has a formula that assigns to every component of the intersection a class of the right dimension in such a way that the sum of the classes is invariant under
So you get a
deformation.
class in S.
So
and then
Fulton
you
will
get
give
gamma.
you a class in S.
And he'll tell you gamma, and then you get gamma.
And then once you take the degree of that class, which is a zero-dimensional class, and subtract it from 7,776, what's left is the degree of gamma. So Fulton's formula, and Fulton works this out, by the way, in typically with Bill, it takes about 3 lines, and it takes me around 3 hours to figure out what the hell went into those 3 lines. but it's there, and you'll see exactly how clean and simple it is. Once you have the whole theory set up. So that's another approach. But, you know, the approach that I really want to talk about today, and I've already sort of said this when I talked about the problem involving twisted cubics on a equivalent threefold, the third approach is to find a better parameter space. This is the classical approach I want to describe. Okay? I'll say what I mean in just a moment, but let me just mention that even within this approach, there are two ways of going about this. I just want to mention this because, again, it's a beautiful construction. If this problem were to arise today, the immediate response, or most people's immediate response, would be, if you want to find a better parameter space, to take the conservative space of stable maps. That's a general way of compactifying a space of smooth curves. And it is, in this case, it takes care of everything. If you compactify the space of smooth conics to the conservative space of stable maps of degree 2 and genus 0 in P2, you'll find that your closures now intersect cleanly in just the points you want, and you can calculate the intersection over here in this space. But this is another topic, and I'm not going to get into it. What I want to show you today is the classical approach, which is the space of complete conics. It's a beautiful, admittedly limited construction, but it's beautiful, and I want to show it to you. So let's do that. Let me say one word before we get started about conics in the plane. And here I'm really talking about smooth conics. If C in P2 is a smooth conic, well, as with any plane curve other than a line, I can look at the set of tangent lines to the curve. And that is what we call the dual curve. It's a curve in the dual projective space. And that's usually denoted C star. So again, for any curve in the plane, we can look at the set of tangent lines. If the curve we started with was not a line or a union of lines, then we get the set of tangent lines. And that's a curve in P2 dual. What's special about the case of conics is that this is, again, a smooth conic. In general, the dual of a curve will be birational to the original curve, but will otherwise not look anything like it. It'll be higher degree, it'll be singular. This is a whole topic for another lecture, which we're not going to have. But in the case of a conic, the dual is again a conic. Okay? And it's not hard to see. Basically, if you ask what's the degree of the dual of a plane curve, you're asking, in effect, if you took a line in the dual projective space, how many points of intersection would that line in the dual space have with the dual curve? That's just asking, if I pick a general point in this P2, how many lines through that point are tangent to the curve? Now, if I have a conic, it's not hard to see that there are, in fact, exactly 2 tangent lines to the conic through the point, through each point. So that says that the degree of the dual is, again, 2. Okay. Where's the, by the way, I can't resist saying this, if the point P were here, where would the 2 tangent lines be? Well, the point is there would be lines in the complex projective plane that are not defined over the reals. They're a pair of complex conjugate lines. And if you write down the equation, I mean, just write down, take your favorite, your circle, take a unit circle, take the point P to be the origin, you can easily see how to write down the tangent lines to the circle through the origin are just the lines through the origin with slope plus or minus I. So, you know, you have to get used to this idea and appreciate that, you know. But this is again a smooth conic, and the last thing I want to say here is a fact that is true for arbitrary plane curves other than lines, which is that the dual of the dual is the original curve. Okay? And again, that's not hard to see if you think, at least in terms of pictures. This is, by the way, again, this is true for a curve of any degree. One way to say it is, if you think of a tangent line as a limit of secants. In other words, if I start with a point P here, I can describe the tangent line as the limit of the secant lines joining P to points, other points on the curve, as that other point approaches the point P. Okay? That's the tangent line. Now, if I apply that same construction to the dual curve, what I'm saying, in effect, is, and you have to do this translation yourself, if I start with a point P on the original curve, and I have a point Q, and I ask myself, if I draw the tangent line to P, so that's the corresponding point on the dual curve, and I draw the tangent line at Q, and that's that line is the corresponding point on the dual curve. The secant line to the corresponding points on the dual curve corresponds to the point of intersection of those 2 tangent lines. As Q approaches P, all we're saying is that point of intersection also approaches P. So that's the content of this statement, but it's when you first say it, it looks remarkable. It is remarkable. All right, so having said that, let's go back to our original problem. Let's just get this thing set up. I'm not sure we're going to get the answer today, but we'll get it set up. And it's not hard to get the answer once we have a good setup. We all know it in 7 minutes. So let me describe the space of complete conics. The basic problem here is, when we go to the original problem, we look at smooth conics, right? And then we compactify them to the P5 of all conics. The problem is that we don't know what the tangent lines to a double line are. A double line appears to be tangent to everything, because it simply can't have a transverse point of intersection with anything. It's everywhere non-reduced. So what do we have to do? We have to keep track of the tangent lines. What that suggests is the following, okay? Look at, well, again, P5 is the space of conics in P2. I want to denote by P5 dual the space of conics in P2 dual. That notation sort of suggests that these are dual projective spaces, and they are, but just, I don't want to get into that. Just think of this as a notation for the space of conics in P2 dual. Okay? Then I want to look at the set of pairs consisting of a conic and in P2 and a conic in P2 dual. This is sitting inside the product of P5 cross P5 star, such that C and C star are smooth, dual, and smooth and dual. Okay. mean, one way to think of this, if you like, is we have a map, a rational map from P5 to P5 star that sends a smooth conic to its dual. This is the graph of that map. And what I'm proposing to do now is simply take the closure. That's our space of complete conics. This is capital Phi. We're going to call it capital Phi. And a point in phi is called a complete conic. So this is the space of complete conics. You see, the idea here is that when a conic approaches a double line, the limiting position, we know that if we have a family of conics approaching a double line, each conic in our family has a one-parameter family of tangent lines, a dual curve. And those dual curves will have a well-defined limit, at least in a one-parameter family. So we want to keep track of where that is. And I will show you now how this space does that. But basically, just to sort of put this into context, what we're going to do is, once we've established some basic facts, since we're not going to finish this today, let me at least outline the program. And it's pretty straightforward once you have this parameter space. So we're going to describe this space. That's a prerequisite for everything that follows. The key is then we're going to, for a conic C, let's say CI, since they're the ones that we're going to be interested in, we let ZCI tilde be the closure of the locus of smooth conics. So C star in phi, such that C and C star are smooth. So this is in the original open subset of pairs of smooth dual conics, and C is tangent to CI. So I'm going to take the hypersurface that I'm interested in, smooth conics, tangent to CI, and I'm going to take the closure not in P5, but in this, so to speak, larger variety phi. And then we're going to show that the intersection of these guys is exactly the finite set of actual solutions. That these have no intersections except in this open subset of smooth conics. By passing to the space of complete conics, in other words, we've eliminated the problem of excess intersection. We have to show that. Once we've shown that, once we've seen that the intersection in this space phi is what we're looking for, then the program is by now standard. We want to find the Chow ring of the space phi and calculate the top self-intersection. The class of ZCI. So the only thing that's different here in some sense from what we were going to do naively, what we did naively and which gave us the wrong answer, is that we're working with a different space of conics. So,
What's the relationship between this space phi and the blow-up of S and the computer space?
they're all the same.
Well, they're all the same.
They're all the same.
Oh, okay.
After the fact, now, it's. I don't mean to step all over the punchline. It's not really a punchline. The point is, as it turns out, and that's a point worth saying, this space can also be realized simply as the blow-up. This is the same as the blow-up. You think about it. This sits inside P5 plus P5 star. It's again, just the graph of the rational map from P5 to P5 star sending a conic to its dual. So of course, sitting inside P5 plus P5 star, it admits a map to P5. And as I will show you now, no, I won't. Well, it's 10:59 by my phone. So I think, let me just say this, and then we'll start next time by doing this out in full. We have a map with a P5, this map is one-to-one over the space of smooth conics. It's also one-to-one over the space of line pairs. It's only over the locus of double lines that we have positive dimensional fibers. We'll see what those fibers look like next time. And in fact, you will see a distinct resemblance between this space and the blow-up of P5 along the Veronese surface, which, as Robin suggests, is not coincidental. They are the same space. It's also the same space as the consaver space, which is now erased, I guess. So that's something, so another way of, but this is a different way of thinking about the problem. It's blowing up, because here, what we're talking about here is still visibly a parameter space for algebraic geometric objects. And that's a very useful aspect of this description. Okay, so let's stop here and we'll continue tomorrow. Thanks.